Hello and welcome to this Python tutorial. So that's it, we built our model, we fitted the logistic regression model to our training set, and then we predicted the test set results. We used the confusion matrix to evaluate the predictive power of our logistic regression model. That was actually quite fine. We found 65 plus 24 equals 89 correct predictions, and 8 plus 3 equals 11 incorrect predictions. But that's not really the fun way of visualizing the predictive power. What is much more fun and much more exciting is to look at the results on a graph. So that's what we're going to do in this tutorial. We are going to make a graph where we will clearly see the regions where our logistic regression model predicts yes, the user is going to buy the product, and no, the user is not going to buy the product. So let's make this graph. So unfortunately, we cannot make this graph in just one line or two lines. I tried to make it the simplest as possible, but by doing that, I ended up with a little more than 10 lines of code. So what I'm going to do, I'm not going to write the whole code right now because you might fall asleep. So what I'm going to do is I'm going to take the code I prepared to visualize the training set results in my text editor. I'm going to copy it, paste it here, then I will select this code and execute it. We will look at our results, interpret them, and then for those of you interested in how we made such a graph, at the end of the tutorial I will explain how it's making the graph. Okay, so I copied it, I'm gonna paste it now. Here it is, here's the code. So that's 15 lines of code, as you can see. And so since I can't wait to show you the results, we're going to select the code now, and I'm going to press Command and Control plus Enter to execute, and we will see the whole thing behind the logistic regression model. We are going to see the true results and the regions of predictions. So let's do it. Command and Control plus Enter to execute, and here we go. That's the graph. So I'm going to enlarge this, and now I'll explain what to interpret. Okay, so let's analyze this graph step by step. First, let's focus on all the points here. We can see that we have some red points and some green points. So all these points that we see on this graph are the observation points of our training set. That is, these are all the users of the social network that were selected to go to the training set. And each of these users here is characterized by its age here on the x-axis and its estimated salary here on the y-axis. Now, we can see that there are some red points here and some green points here. The red points are the training set observations for which the dependent variable purchased is equal to 0. And the green points are the training set observations for which the dependent variable purchased is equal to 1. That means that the red points here are the users who didn't buy the SUV, and the green points here are the users who actually bought the SUV. So now, as a first step of analysis, let's give an interpretation of what we observe here with these users. Okay, so first, we can see that the users who are young with a low estimated salary, so these users here, actually didn't buy the SUV because these points are the real observation points. They're red, and red corresponds to 0 here. So that means that all these points here are the users who didn't buy the SUV, the users in the training set. Then, if we look at the users who are older and with a higher estimated salary, well, we can see that most of these users actually bought the SUV. And it actually makes sense because the SUV is more like a family car and therefore more interesting for these older users here with a high estimated salary. Besides, we can also see that some older people, even with a low estimated salary, actually bought the SUV. Because we can see that we have some green points here that correspond to an age above the average is here, but an estimated salary below the average because the average is here. Okay, so these guys, these older guys, although they have a low estimated salary, actually bought the SUV. Probably because they've been saving up some money, or maybe they finished paying off their mortgage. I don't know, but what's for sure is that they couldn't resist buying this very cool luxury SUV offered at a ridiculously low price. And on the other hand, we can also see that there are some young people here with a high estimated salary who actually bought the SUV. You know, maybe because it's a very cool SUV and they want to impress their friends and take them into road trips, or maybe they already have a family. I don't know. Anyway, they bought the SUV. Actually, there are a lot of buyers, so this must be a very cool and cheap SUV. Okay, and now what is the goal of classification? Now we're talking machine learning. Why are we making some classifiers, and what will classifiers will do? At least what are we trying to make them do for this particular business problem? Well, the goal here is to classify the right users into the right categories. That is, we are trying to make a classifier that will catch the right users into the right category, which are, yes, they buy the SUV, and no, they don't buy the SUV. And we represented the way our classifier catches these users by plotting what are called the prediction regions. And so the prediction regions are the two regions that we see on this graph, this red one here and this green one here. And the red prediction region is the region where our classifier catches all the users that don't buy the SUV. And the green prediction region is the region where our classifier catches all the users that buy the SUV. But be careful, this is according to the classifier. That is, for each user of this red prediction region here, our logistic regression classifier predicts that the user doesn't buy the SUV, and for each user of this green prediction region here, our classifier will predict that the user buys the SUV. Even if that's not the case in real life, that's just a prediction, but that's what our classifier believes will happen. It is the classifier prediction compared to the truth here, which is the point. The point is the truth, and the region here is the prediction. So that makes an awesome tool because for each new user of the social network, well, our classifier, our logistic regression classifier will tell based on its age and its estimated salary if this user belongs to this red prediction region here and therefore doesn't buy the SUV, or if this user belongs to this green prediction region here and therefore buys the SUV. And that way, this business client car company can substantially optimize their marketing campaign by targeting the social network ads to the users in the green region because these are the users that are predicted to buy the SUV according to our classifier. Now, the other very important thing to understand is that these are two prediction regions separated by a straight line, which is the straight line here. And the straight line is called the prediction boundary because it's the boundary between the two prediction regions. And the fact that it's a straight line is not random. It is for a particular reason, and that's the thing very important to understand because that's the essence of logistic regression. If the prediction boundary is a straight line here, that's because our logistic regression classifier is a linear classifier. That means that here, since we are in 2 dimensions, because we have 2 independent variables, the age and the estimated salary, so we are in 2 dimensions, then since the logistic regression classifier is a linear classifier, then the prediction boundary separator here can only be a straight line. If we were in 3 dimensions, then it would be a straight plane separating 2 spaces. But here in 2 dimensions, it's a straight line. And it will always be a straight line if your classifier is a linear classifier. But you will see later that when we build non-linear classifiers, then the prediction boundary separator won't be a straight line anymore. I won't tell you more right now, and I will let you wait for the surprise. So here, we can clearly see that our logistic regression classifier manages to catch most of the users who didn't buy the SUV in the red region here, and most of the users who bought the SUV in the green region here. So it actually did a pretty good job. However, it seems to have trouble catching some green users here who, in spite of their low salary, bought the luxury SUV, as well as those other green users here who also bought the luxury SUV. Because as you can see, these green points here and those here are in the red region, which is the region where our classifier predicts that the users don't buy the SUV. And those incorrect predictions are due specifically to the fact that our classifier is a linear classifier and because our users are not linearly distributed. If they were linearly distributed, then we will have all the green points here in this space and all the red points here in this space. And then a linear classifier with a straight line could perfectly separate all the red points here and all the green points here. But here we have some rebellious points who are not in the wanted linear regions, and because our classifier has a linear straight line separator, that's why it has trouble catching those users here and those here. You can clearly see that even if you try to rotate this straight line here, well, you will always have some green points in the wrong category. For example, if we try to rotate here this way, like putting it down, well, okay, we will catch these green points here in the right green region here, but since we rotate it down, we will take more green users here because this will go up and more green users here will be in the red region. So that's the best separator the logistic regression classifier could find, and it couldn't do better because it can only be a straight line separating these two regions. Because to catch those users, the green users here and the green users here in the right category, that is the green region, our classifier would need to make some kind of a curve here to, classify correctly those green users here and place them in a green region. And that would prevent our classifier from making this incorrect predictions here because it is a straight line. With a curve here, we would catch all the red users properly in the red region and all the green users in the green region. So that would make an awesome classifier. And you will see how our nonlinear classifiers will make a terrific job at doing this. I can't wait to show you this. Okay, and now eventually the last thing very important to understand is that this is the training set. This is a training set, so that means that our classifier learned how to classify based on these informations here. So I would hold my breath a few more seconds until I find out if our logistic regression classifier can manage to make good predictions of new observations, that is to classify new users into the right regions, which by the way are fixed regions here because these are the regions generated by the learning experience of our logistic regression classifier and therefore won't change if we look at some new observations, that is new social network users. And that's what we are about to find out on the test set. So hold on. So what I'm going to do now, I'm going to copy this because we want to be efficient, and paste it here. And now I'm just going to replace training here by test. All right. And here I just have to replace xtrain by xtest and ytrain by ytest. That's all. That's all I need to do. Oh, and maybe the title. I'm going to change the title of the graph test. Okay, so let's now see how our logistic regression classifier predicts the new observations on the test set on which our model wasn't built. So Command or Control plus Enter to execute, and let's see. All right, not bad, not bad. I'm going to enlarge this. Here we go. So this looks good. This looks very good. These are the real results in red. That means the users that didn't buy the SUV in reality, and these are the customers that bought it. And we can see that the prediction regions predict well those real values because all those red points here are in the red region. So that's the correct predictions. All those green points here are in the green region. So that's some other correct predictions. And of course, since this is a linear classifier, the logistic regression makes a few mistakes here, but that's fine. And that's actually the incorrect predictions we saw on the confusion matrix. Remember, there was 11 incorrect predictions. We can count them here. This green point should be here, so it's 1, then 2, 3, 4, 5, 6, 7, 8, and then we have to count the red points in the green region that was incorrectly predicted. So 9, 10, and 11. Okay, so yes, that's the 11 incorrect predictions that we found in the confusion matrix. All right, so that's the first classification model we built. I hope you like the graph. Okay, so congratulations, you implemented your first classification model on Python. In the next tutorials, we're going to do it on R. And now for those of you who are interested in understanding how the graph was made, stay with me and I will explain right now how it works. Okay, so the best way to explain it is to reselect this. Command Control plus Enter to execute. And here's the graph. So what is the idea? How did we plot those prediction regions? Well, the idea is actually pretty cool because we took all the pixels of this frame here. That means this pixel, all the pixels, but actually with a 0.01 resolution. So we took all the pixel points of this framework and we applied our classifier on it. And so, it's like each of these pixel points is a user of the social network with a salary and an age. So it's like an observation, only it's not the observations we have in our data set. It's a new observation we create. But we have to picture this like a user in the social network with an estimated salary and the age. So for each of these new pixel points, these new pixel observation points, we applied our logistic regression model to predict if this pixel observation point has value 0 or 1. And if our classifier predicts 0, then it's going to colorize this pixel point in red. And if the classifier predicts 1, it's going to colorize the pixel point in green. So by doing this on all the pixel points in the frame here, it colorizes all the pixel points that have the 0 predictions here, and all the pixel points that have the 1 prediction. And since the logistic regression is a classifier, the limits between those sets of points is a straight line. Because as I told earlier, the logistic regression is a linear classifier, which means it's a straight line in 2 dimensions. And now that you understand that, you will understand this code very well. Okay, so now let's go through the lines one by one. We start by importing the listed column map class that will help us colorize all the data points. Then we create this line to just create some local variables xset so that we can replace xtrain and ytrain easily by xtest and ytest instead of having to replace it everywhere because we use xset several times. So there's just a shortcut to avoid having to replace too many times the xtest and xtrain here. Okay, here with these 2 lines of code x1 and x2 equals np.meshGrid, we prepare the grids with all the pixel points that I just talked to you about. So here, as you can see, we take the minimum values of the age values, -1 because we don't want our points to be squeezed on the axis here, and the maximum values of the age, to get the range of pixels we want to include in the frame. And same for the salary, we're taking the minimum salary -1 and the maximum salary +1 to get all the estimated salary range and -1 and +1 so that the points aren't squeezed. And here we're choosing the steps 0.01, that means that there is a 0.01 resolution. So for example, if I had chosen 0.5, this wouldn't have been that dense. We would actually see the pixel points. But that's better to take this resolution because these are nice prediction regions. It's like it's continuous. Okay, and then with this line of code, that's where the whole magic happens. Because this is where we apply the classifier on all the pixel observation points. And by doing that, it colorizes all the red pixel points and all the green pixel points. And we use this contour function to actually make the contour between the two prediction regions, the red one and the green one. Then as you can see here, we use the predict function of our classifier, the logistic regression classifier, to predict if each of the pixel point belongs to class 0 or class 1. Then if the pixel point belongs to class 0, it will be colorized in red, and if the pixel point belongs to class 1, it will be colorized in green. Okay, so here we plot the limits of x, the age, and y, the estimated salary. Then with this loop here, we plot all the data points that are the real values. So all the red data points here and the green data points. So we're using this plt.scatter, which is what we use from matplotlib to make a scatter plot. And then very simply here we add the title logistic regression training set, the x label age, the y label estimated salary. We plot the legend to specify that the red points correspond to 0, that is the user didn't buy, and the green point corresponds to 1, that is the user bought the product. And plt show to display the graph and specify that this is the end of the graph. Alright, so congratulations if you're still here. Congratulations for having the curiosity of wondering how we can build such a plot. So that's a lot of things to learn in this section, because you learned how to make a logistic regression model and how to make an awesome chart. So congratulations. After we do the same thing on R, in the next sections things are going to get even more exciting, because we will build even more powerful classifiers. So I look forward to showing that to you.